welcome to HEI's first ever concurrent sessions. I've been asked to remind you, you're in the TRACER session, so hopefully that's where you're meant to be. Just waiting for the slides to start up. You've all heard from me, Donna Voorhees. And I want to just start the session by explaining slightly more than I did in the morning session. The Energy Research Committee reviewed a lot of great research applications, and 3 of those applications emerged as the best. And in fact, the committee thought to go one step further and basically to force a collaboration among these teams, whether they liked it or not. And that became the TRACER collaboration, thinking this was really the best way to answer some of the questions that were being asked around, what are the exposures? How do we predict exposures going forward? Even as the world keeps changing, the industry keeps changing. The model really is the central focus of a lot of the research. The idea here and the goal here early on from the committee was to create something that could be used not only in the study locations, but be adapted for use more broadly across the US and be more broadly helpful to the policy decisions that are being made everywhere. So that's the beginning of it. They also did, the other thing is they did the air quality and noise monitoring. That was to understand exposures right in the study locations, but also to use those data to evaluate the model. And then finally, NASA HAQAST Tiger team did some terrific complementary work, and we'll hear about that today too, where all of the TRACER teams were doing ground-based monitoring, air quality and noise monitoring. The TRACER Tiger team, led by our own Ted Russell from the research committee, they analyzed satellite data that complemented the work, same time, same place as the monitoring that was going on the ground. So that's what you're going to hear about from this morning in a broad scale. I want to introduce our co-chairs for this session, and they in turn will, I'll turn it over to you and they'll introduce all of the speakers. But with us is Dr. Christine Wiedinmyer. She's the Series Associate Director for Science and Research Professor at the University of Colorado at Boulder. She previously served as a scientist at the National Center for Atmospheric Research, and her expertise in research involve air pollutant emissions and their impacts. And we're very pleased to have Dr. Wiedinmyer as a member of our HEI Energy Research Committee, HEI Energy Review Committee. And Dr. Ted Russell is in the School of Civil and Environmental Engineering at Georgia Tech, where he studies air pollution dynamics and the linkage to health. We're also very lucky to have Dr. Russell as a member of HEI's Energy Research Committee. Christine and Ted, take it away.
Thank you, Donna. And actually, I really want to thank Donna for overseeing the Energy Research Committee all these years. And I think much of our success really stems from Donna's keeping us on track. So with that, I'd like to introduce our first 2 speakers today. Coming from the University of Texas at Austin. The first is Dr. Leah Hildebrandt Ruiz. She's an associate professor in the McKettis School, Department of Chemical Engineering at the University of Texas. Her research focuses on the formation of air pollutants, their transformation, and atmospheric fate to make better informed recommendations for environmental policies aimed at improving air quality and human health. Towards this goal, her team uses advanced instrumentation and a combination of laboratory experiments, field measurements in the outdoor and indoor environments, and modeling. She's going to be ably assisted by Dr. David Allen, who is the Norbert Dietrich Welch Chair in Chemical Engineering, where he has been the lead investigator for multiple air quality projects in the unconventional oil and gas development area. He was elected to the National Academy of Engineering in 2017, and in 2020, he was recognized with the HEI Energy Transition Award, which has been referred to as the Nobel Prize in Energy. From 2012 to 2015, he chaired the U.S. Environmental Protection Agency's Science Advisory Board. So with that, Leah.
Thank you, Ted, for the introduction, and to HEI for organizing this research. So I will tell you about our work, taking measurements and modeling to evaluate community exposures to air pollutants from unconventional oil and gas development. We have a fairly large research team that I had the honor of leading, mostly at UT Austin and also at George Mason University. These headshots here are just the PIs and co-PIs of the work. We have a large team also of graduate research students, as well as other researchers who have been working on much of this work. And several of them will be giving posters this afternoon, and we'll point out several of these posters throughout this presentation. So the main goal of our research was to generate this community model that can assess exposures to air pollutants from oil and gas development and inform future health studies. This model is called the TRACER model, coming out of the TRACER collaboration, and it combines an emissions model with dispersion modeling. We also can, and we have coupled this emissions model to chemical transport modeling as well. As part of this work, we also took targeted field measurements in part to evaluate and to refine the model. We evaluated exposures and can use that to inform future health studies. The original focus of our work was on the Eagle Ford Shale, and the project was then expanded to also do some modeling in the Marcellus and additional measurements in the Permian Basin. So I'm going to start by talking about some of our measurements that we took in the Eagle Ford Shale. So this is a map of the Eagle Ford Shale in basically these colorful regions. The star is the location of Karnes City, which is located in the middle of the Eagle Ford Shale. And our measurement location in Karnes City was just outside of town. We took stationary as well as mobile measurements. So the stationary measurements, we basically have instrumentation set up in the stationary trailer. We took measurements over the course of several weeks in 2 different seasons. And then for mobile measurements, we used our mobile van, which basically is allowing us to get closer to the source and measure a greater number of sources. This is what some of these mobile measurements look like. So what you're seeing here is the background is a satellite image of the region. So here you see Karnes City, as well as some of the other towns pointed out in yellow. For those of you not familiar with the area, the white rectangles, the numerous white rectangles you see on this graph are all oil and well pads. So it gives you some sense for the density of activity in the region. And these are data, VOC data from the VOCUS PTRMS that are plotted. So benzene is in blue, toluene in red, and then C8 aromatics, the sum of xylene and ethylbenzene, is in yellow. And what you can see here is that as we're driving around in the area, that we are sampling several of these sources where we see enhancements of these pollutants. You can also already see that the ratio of the pollutants differs quite a lot by source. So sometimes you see benzene dominate, sometimes C8 aromatics, and some other peaks have fairly even distribution between toluene, C8 aromatics, and benzene. And this is just a photograph through our, through the dash cam showing as we approach one of these flaring sites. This is more like another summary figure, the map of all of the sites may be measured. So here you have the tracks that we followed, and then the circles are the 34 different flares that we sampled over this campaign. And just to show you some example data, this is a short time series from one of the flares we measured where you see enhancement in, here we're plotting benzene just as an example, as well as methane and CO2 indicating the presence of this flaring plume. There is also a possibility of us measuring other sources at the same location. So we conducted factor analysis to separate the flaring plume from other emissions. And Evelyn is presenting a poster this afternoon with a lot more details on this analysis. Talking a little bit about the stationary measurements. So this is several weeks of data from the stationary side in Karnes City. This is co-located with a TCEQ monitoring station. So in this figure, actually, the methane data are from us. The VOC data are all from the TCEQ GC monitor. And what you can see in this figure is a great variability of concentrations over the course of these weeks. And all of these peaks happen to be in the early morning, something like between 3 and 6 a.m. So we've done a lot more analysis, modeling analysis and further analysis of the data. that basically go to show that these peaks can be due to routine emissions combined with favorable meteorology, or they can be due to emission events. We also took measurements of PM at the stationary location. These are data from our aerosol chemical speciation monitor showing both the concentrations and the bulk composition of the PM. I do want to point out, while these levels are all below national ambient air quality standards, these are fairly high levels for this region that really doesn't have any other sources than oil and gas development. So it's an indication that the emissions from oil and gas are influencing air quality and are influencing PM. These two periods were periods when air was coming from the northeast, and it turns out that in the northeast there's a high well density and also more wells that are oil wells rather than gas wells influencing this air. And this afternoon, our PhD students, Kat and Leah, are going to be presenting a poster on these stationary measurements in Karnes City. We also took measurements in the Permian Basin. This is an overview figure showing you data of methane and benzene that we took while driving around in the Permian. And it points out basically hotspots that we measured, both of benzene and methane, and those hotspots correlating with each other. Also not directly shown on this figure is that we did see quite a few differences between the Permian Basin and the measurements and the Eagle Ford Shale as well. Chief among them is that we saw much higher concentrations of hydrogen sulfide in the Permian than in the Eagle Ford Shale. And Daniel's going to be presenting a poster on this afternoon. So to summarize some of these findings from our measurements, we saw high diurnal variability of VOC concentrations with highest concentrations at night, which also results in variability then in exposures. Emission factors and destruction efficiencies from the flares were highly variable, and we ended up using median values as well as high and low values in our modeling. We see differences between our observations in the Permian and the Eagle Ford Shale, and you can learn a lot more details about our work in the posters this afternoon. And with that, I'll turn it over to Dr. Allen for a discussion of the modeling.
Thank you, Leah. So what I'd like to do is talk with you a little bit about how we use models to put these measurements that are spatially and temporally explicit in context. And I'll begin with just talking about what do we need in these models? What sort of spatial and temporal resolution do we need? And so this starts with looking at methane emissions from an oil and gas region in north central Texas in a region called the Barnett Shale. And the white lines here are counties. This is hour-on-hour methane emissions shown. And the message from this plot is that these emission models that we're going to be developing and that we have developed through the TRACER program need very high spatial and temporal resolution to capture all these features. We need emissions not just for methane, but for multiple species, and we need to characterize differences in emission compositions for various different types of sources on oil and gas sources, and then build user-friendly models for all these. In the short time available, we can't explain to you all of what we've done, but I'd like to give you some representative results. First, let's look at applying this type of model then to create a different version of these inventories, in this case, time series. These are time series of 4 different chemical species in a particular county in the Marcellus Shale. And what I want to point out to you is the temporal variability. Going clockwise from the upper left, you have methane, then ethane, then total VOCs, then NOx. And I'll repeat, this is at the county level. If we aggregate at the grid cell level, say 4 kilometers by 4 kilometers, the difference between the maximum and the mean is not going to be a factor of 2 or 3 or 4. It's going to be a factor of 100. High spatial and temporal variability between maximum release rates at the hourly level and median release rates over the course of on the order of an hour. So if you want to learn more about this variability, see Dr. Chining Chen, who has a poster this afternoon. So if we develop these highly resolved, spatially and temporally resolved inventories of emissions of various chemical species, what will that reveal? How do we use that information? I'm going to give you a number of examples, but just to give you a taste of this, what you see in the upper plot here is a time series over the course of several months to a year of hourly concentrations measured at a particular site, in this case in the Eagle Ford, the Karnes City site. So we're going to need, in the atmospheric models that we couple with the emission models, high spatial and temporal resolution. We're going to need to understand the boundary layer behavior, the buoyancy and the release heights of different sources, and so on. Again, building user-friendly tools. With the limited time in this session, I'm not going to be able to give you all these features, but I'll just pick out 3 examples and then refer you to posters that will be available this afternoon. So first, how big a modeling domain do we need? And again, an image of the density of sites is shown on the left here. Leah pointed to this earlier, a very high density of source sites. There are more than 20,000 source sites in the Eagle Ford. And so if we're going to understand a central receptor point, much like we do currently in chemical transport models for things like ozone, we need to model a very large area. If we look at mean values measured at that central point, in this case for one particular pollutant, and it varies by pollutant, only about 15% of the sources that account for the mean value are within 5 kilometers of that central point. Within 10 kilometers, we get about half of the mean accounted for. We need to go out to quite large distances because there are so many sources to be able to explain the mean. So do we really need all this level of detail? What do we get from this level of detail? And I'm going to give you an example that builds on what Donna described very briefly in the plenary session this morning. So does this matter, for example, in SIP planning? Right? Do we need to account for this variability as we look at, for example, regional photochemistry and ozone formation? Well, let's look at one particular source. In this case, drilling or hydraulic fracturing or things that occur prior to production. Those only occur at a limited number of wells. Typically, what we do right now in planning is we take averages over counties and we average over an entire year. And then we calculate emission rates and put that in our photochemical models and attempt to explain the photochemistry. But what's really happening is at any given moment in time, any given hour, there are only a small number of wells that actually have those emissions of drilling or hydraulic fracturing, and it's only operating for a certain amount of time. So even if we keep the emissions exactly the same over the course of a year, we can change the emission rate at a single well site by a factor of 3 orders of magnitude at any given point in time. And if that point in time is during ozone conducive conditions, and you have, like you do in the Eagle Ford, large amounts of biogenic VOCs, the impacts on ozone can be substantial. Here you see our predictions on the bottom right of the variability in the NOx emissions from day to day that we estimated based on when the drilling actually occurred. And above that, mappings of what the changes in maximum daily average 8-hour ozone concentrations. Substantial. And this is what it looks like over the course of the month of August. If you'd like to hear more about this NOx variability, see Suar's poster later this afternoon. Final example, how do we determine the relative importance of meteorology and emission events in driving acute exposures hour on hour? So let's again go back to that location at Carnes City in the Eagle Ford. Here you have a 1-year time series of ethane concentrations measured at that site. You see very similar behavior for things like benzene. And what you see below that is the time of day distribution of the 99th percentile of those concentrations. So all the concentrations, all the very highest concentrations are occurring at night. So what's causing that? Is it meteorology? Is it routine emission events coupled with the meteorology? Is it extreme emission events? So we've evaluated those causes and determined that what is happening is likely two things. One is we do have non-routine emissions, things that we can't explain with the meteorology and the routine emission predictions, but we also have a large fraction of these events that are explained by the coupling of nighttime meteorology with routine emissions. And so here is a comparison of routine emissions, meteorology, together with observations. We see places where we match things with routine observations well, and we see things where they don't match up well. It's complicated, but the good news is this TRACER collaboration is developing the tools that are allowing us to unravel this. If you want to see more details about these matchings of fixed point observations with emission models and dispersion models, you can see Joel's poster in the afternoon. So I've tried to highlight 3 findings of coupling these emission models with various atmospheric models to give us insights. And now Leah is going to talk a bit more about using that to estimate exposures.
Thank you. So this work on the exposure modeling was primarily done by our colleague Lucas Henneman and his group, and he has a poster also this afternoon talking more about this. But basically for the exposure modeling, our goal was to evaluate exposures to air pollution from unconventional oil and gas development in Karnes County, seeing how many wells there are and how large of an area we need to consider. We also evaluated the use of lower complexity dispersion models and wanted to evaluate exposure equality. And so here is one of the basically results slide as an example. So this shows Karnes County and the concentrations, in this case, of ethane as a representative VOC emitted from oil and gas development during the night and during the day. So first of all, this shows the great difference between daytime and nighttime exposure to VOCs from oil and gas development in Karnes County. And it shows you where the hotspots are, and also that overall that the exposure happens across this band, across Karnes County. Now we can now go back. Remember, we started with an emissions model, so we can go back and calculate what sources these concentrations were due to. And so this is the same map, separating it into different sources of emissions from oil and gas development, showing that most of the concentrations are due to emissions from tank flashing, pneumatics, and liquid unloadings. Now, again, we wanted to evaluate the impact of the ability of lower complexity models to represent some of this variability of exposures. And so the models we used, or that Lucas's team used, the least complex one is this inverse distance weighting, where simply concentrations decrease as the inverse distance from a source. And that's the simplest model. The reason we wanted to test this is not because we thought it would be representative, but because it's a model that's still getting used to evaluate exposure. Then the next level of complexity was inverse distance weighting, considering the meteorology, the primary wind direction, and then we have a Gaussian single equation formulation, CalPref, AirMod, and comparing that to observations. So what this is showing, as an attempt to summarize all the variability and the range of data we have, this is showing the day-to-night ratio and the observations, and then from the different modeling results. So of course, this feature is doing everything as inverse distance. We are not really capturing the day-to-night ratio, but even this inverse distance model, just considering the predominant wind direction, does pretty well in capturing the differences, again, between daytime and nighttime exposures. And this is basically just showing the same thing as a time series. Finally, we can use these data to look at equality of exposures. And again, there's a lot more detail in the poster this afternoon. In this figure, we are just showing the exposures as a function of income, so low, mid, and high income in the day, which is in green, and night, which is in orange. So one of the things I wanted to point out is that overall, the day-to-night variability is larger than the variability with income or other factors that we looked at. So everyone is exposed much more at night than during the day. Our results actually indicate that wealthy populations and white populations, which is not shown on here, have the highest exposure, and that's basically due to where they live. So the wealthy populations in the Eagle Ford Shale live in the Northeast, and that's where there is a higher density of wells and also more oil versus gas production. So as an attempt to summarize all of our findings, so we see high diurnal variability of exposure with highest concentrations at night. We also see a higher variability of emission factors and destruction efficiencies from flares and use median values in our modeling. Modeling exposures from unconventional oil and gas development emissions is highly complex due to the number of sources, the high spatial and temporal variability, and to the need to model all sources in at least 50 to 100 kilometers. Now, we did do it. The TRACER model can do that and can evaluate exposures to oil and gas development emissions. But if you have a need for a lower complexity and lower computational burden, there's also the possibility that some lower complexity models can capture some of the important variability that we see from our more complex models. And with that, I thank you for your attention. We'll be happy to answer questions later.
Thank you very much. And just as a reminder, we're going to save questions for a Q&A session with all of the speakers afterwards. So it is my pleasure to introduce Dr. Meredith Franklin of the University of Toronto. She is a leading expert in developing advanced data science tools and artificial intelligence models for environmental exposure assessment. With a strong interdisciplinary approach, her research integrates machine learning, statistics, geospatial analytics, atmospheric science, and health. By leveraging vast multi-source data from ground and space-based sensors, her work plays a crucial role in facilitating and improving environmental epidemiological studies and public health risk assessment.
Hi, thanks for having me. And yes, I do a lot of modeling, but today I'm going to speak about a lot of the measurements that we did in our study assessing source contributions to air quality and noise in unconventional shale plays. Is this one?
Yeah. Just as a reminder, it's 15.
Okay, so our study motivation, we saw this boom in the region of the Eagle Ford Shale and the Permian Basin since 2010, where oil and gas production has increased over 8-fold since 2010. Coupled with this, we've seen an increase in the density of gas flaring in the Permian Basin and the Eagle Ford Shale, which has reflected oil exploration. And the map on the right is based on satellite data of flaring that we've observed in the region. So our study was really to leverage measurements and some modeling as well. We did a very intensive measurement campaign in the Permian Basin where we collected air quality, greenhouse gas, radioactivity, and noise data at high temporal resolution from a stationary monitoring platform in the Permian Basin. You can see we were located in New Mexico. That's our trailer, the inside of our trailer. And we were in Loving, New Mexico, which is on the western edge of the Permian Basin. We collected data from May 1st, 2023 through May 31st, 2024, so just over a year. And we collected a whole host of things, as you can see here from the long list of the compounds that we collected, including the air pollution, greenhouse gases, radioactivity, and noise as well. We coupled this with a passive monitoring sampling campaign to understand the spatial distribution of targeted petroleum hydrocarbons in the ambient air. So we deployed passive samplers both at the same time as we were collecting the high temporal resolution data in the Permian Basin. So between June 2023 and June 2024, we collected data with the help of 6 community volunteers that hosted these passive samplers. And then we had one that was co-located with our trailer. And then we after our targeted campaign finished in the Permian Basin, we moved to the Eagle Ford Shale, where we collected data from 4 community volunteers that hosted the samplers, and then one site in College Station. And that was done at a later time. So with all of this data that we collected, I'm just going to describe a few of the methods that we use to analyze the data. So for the stationary monitoring data, we worked a lot looking at time series plots, polar plots. And then we also did a comparison with the Denver-Julesburg Basin data that is collected by Detlev Helming, one of our team members. And the map that you see is showing the well density with respect to the monitors that we compare our data to. Then we did a source apportionment with non-negative matrix factorization, which I'll show. We did regression modeling with the satellite flare observations. We also looked at noise frequency analysis. We used machine learning for that. And then for the passive sampling data, we looked at the spatial temporal trends in that data. And we also did comparisons there, but we compared to the TCEQ monitors and with data from large cities in Texas. And then we also did a correlation analysis with well density. So some of the major highlights from the study, we saw methane. This is showing methane from the L&M stands for our stationary site in Loving, New Mexico. So from the methane data, we saw this time series that showed frequent high concentration plumes, seasonal changes with higher concentrations in winter due to reduced atmospheric mixing and lower sunlight. We also saw the methane plumes that were depicted above the 95% confidence interval here that were seen at all times of day. But we did see that median levels at night, again, were around 3 ppm, which is 50% above the background levels. This is our source apportionment results. So we ran non-negative matrix factorization. We resolved 5 source factors that explain 96% of the overall variability in our data set. And we determined these 5 sources to be from traffic emissions. I've put the percentage that relates to the amount of the variance for each of these sources. Combustion from engines, turbines, and compressors, which was in yellow, which we saw really dominated by CO2. And then oil and gas fugitive emissions, which was of the 5 components responsible for the largest amount of variance explained. And from that, we see that it was dominated by alkanes. And then finally, we found 2 source factors that were related to flaring. So related to the ozone that we saw as well, which I'll speak about in a second, we really, with the non-methane hydrocarbons, we saw that carbon hydroxy radical reactivity was really driving ozone formation potential. And it was the largest contributor to the regional photochemical ozone formation from these hydrocarbons, the alkanes that we saw. So from this pie chart, you can see that the hydrocarbons associated with oil and gas, particularly the alkanes, are representing 88% here in that pie chart, were really driving the ozone formation potential. Further to this, we looked at a couple of specific sources here with ethane. So we saw that the ethane was really quite a lot higher than any of the DJB sites. And the other motivation here, we see the pentane ratio, the I to N pentane ratio, which was less than 1, which further confirmed our regional methane and hydrocarbon concentrations were almost entirely driven by the UOGD related sources. In terms of ozone, we also see that nitrogen oxides can drive the ozone formation. And as a comparison here, we had a few of our DJB sites as well. We included 2 urban sites. So we see that the nitrogen oxides in Loving, New Mexico was also quite high, higher than Dallas, and comparable with Houston, a large city where, as we know, traffic-related pollution drives nitrogen oxides. When we look at it by wind direction at our site, we see the sources from the city itself. We also see this peak from our neighboring well pad site, as well as the flaring source and the highway. There's a transport highway, Highway 285, the main transport highway within the Permian Basin that was very close to our site. So now to ozone. During daytime, we know that ozone can peak, especially from noon to 6 p.m. during clear skies, warm temperatures, dry conditions. And typically since 2018, Southeast New Mexico has exceeded the 70 ppb NAAQS threshold for ozone levels about 20 to 30 times per day, days per year. And we saw something very similar. So our measurements were taken at 1 minute. So on the left, we see the 1 minute measurements with lots of exceedances there. But when we do the regulatory comparison with the 8-hour average data, we found during our year-long sampling campaign that 39 days were exceeding the 70 ppb NAAQS during our sampling period. And now if we think about the regulatory action on this, the EPA uses the design values for that. So what we found, so this is an analysis of the design values for the historic, from historic data, which were used, so the EPA in this region uses the Carlsbad Caverns National Park site, which is nearby, but we can see from the blue dots how that has increased significantly since 2018. And then when we use our data to calculate that design value, you see that we're way off the charts here. If we were to use our site for the design value, it's at 86.8 ppb. Another interesting thing that we did was look at radioactivity. So radioactivity, hydraulic fracturing can mobilize radioactivity from the soil. And so this is a concern, and we were interested in looking at this very novel metric of exposure. What we found for the total radioactivity is that it was highest during low to moderate northwest to northeast winds. Winter values were higher as well. And then we also saw that the total radiation is approximately 2 times above the typical background levels in our region. We can see where the indoor action level is quite high. Our concentrations were lower than that, but we do see here the gray bar showing the continental background in the outdoor air. And so our concentrations were higher than that. Now, noise. We haven't heard much about noise. We did do quite a deep analysis of a noise frequency data. The interesting findings from this were that it was dominated. So the plot is just the time series of the weighted. So noise is a little complicated because noise, we can get individual frequencies, but then what we normally see analysis of are the weighted frequencies. And so on the left, the time series plot is showing the LC weighting, which emphasizes the low frequency noise was quite a bit higher and dominated our noise measurements in the region. We can also see that from the plot on the right, where the low frequencies were dominating, particularly at night. And so so low frequency noise is related to sleep disturbance. It has been associated with a stress response. And as a result, cardiovascular responses. So we really see the dominance of the low noise from things like compressors, for example. And we did this machine, so the text on the right is a little hard to see. We did an analysis looking at the relationship between the noise frequencies and the pollutants. And so this really pointed that we saw, it's hard to see the numbers here, but we saw this very strong association with CO2, suggesting a combustion sort of base source with the compressors and the mechanical processes that are producing CO2 as well concurrently with the low frequency noise. Now onto the passive sampling distributions. So we can see, so this was really to look at the spatial distributions. So what we saw here was this clear gradient spatially. So the line is pointing towards our LNM site. We see the density of the wells. And we just see that, so this is methyl cyclohexane concentrations, which are a typical oil production related hydrocarbon, and showing those strong gradients spatially, and it's related specifically to well density. So the correlation matrix above is showing the correlation at different buffers around these sites with relation to the number of wells. And we see a strong correlation with benzene and methyl cyclohexane with the number of wells that are located in those buffers. The passive sampling results also showed temporal trends. So we see the strong temporal trend in the benzene concentrations from our sites. We see that, that it's very seasonal. And then on the right, we see the comparison with the other sites in Texas. So we do see that our site level benzene distributions were quite a bit higher than some of those in the other sites in the Texas urban areas. So in summary, based on our continuous air monitoring and loving, we saw that the oil and gas development really completely dominated the methane emissions in the area. Methane plumes are really a good indicator of industry-related pollutant emissions. Our county, Eddy, New Mexico, has been exceeding the ozone max, and our data and others have suggested this regional ozone problem, which is largely due to very significant VOCs emissions from oil and gas operations in the region. And then comparing our data with other prior monitoring results suggests that the ozone pollution levels are increasing and defying trends in other areas of the US. The passive network really showed us these clear gradients again of the oil production hydrocarbon markers and benzene that were related to well pad density, particularly in the Permian Basin. Seasonal changes in all of the hydrocarbons were more pronounced in the Permian Basin than the Eagle Ford Shale. And then concentrations in the Permian Basin were also higher than those of the urban monitoring sites in Texas. So overall, this study, to the best of our knowledge, is one of the most extensive air monitoring campaigns in the Permian Basin. And in comparison with the Eagle Ford Shale results, we've seen that our measurements are very complementary to the prior work that's been done in this area. And that is big thanks to all of our team. So we also have several posters. So Gunnar and Detlev and I are here presenting posters this afternoon. And we really thank the HEI Energy for sponsoring this work. And Jill and Laura have done a lot of the work with the community volunteers and relaying our work to the community that we've been sampling in. So thank you.
Thank you, Meredith. Our next speaker today is Dr. Jeff Collette. He's the University Distinguished Professor of Atmospheric Science at Colorado State University. He's a fellow of the American Meteorological Society, serves on the National Acid Deposition Program Executive Committee and Colorado's Regional Air Quality Council. He is currently the chief editor of the Journal of Air and Waste Management Association as well. His research includes nitrogen deposition, regional haze, ozone formation, cloud chemistry, and air quality impacts of oil and gas development. So with that, Jeff.
Thanks, Ted. Really happy to have the opportunity to join my colleagues here in the TRACER collaboration to tell you about some of the work that we've done over the last 3 years, funded by HEI in the Denver-Julesburg Basin in Colorado. And a little bit different than the other studies you've heard about, we are really focused in close on individual oil and gas well pad development. So we looked at noise, which I won't talk about today. But we also were looking at air toxics and other VOCs emitted from especially pre-production operations, which have received a lot less attention in the scientific community than longer-term oil and gas operations. I want to acknowledge my co-authors or the study participants on this from Colorado State University and the Colorado School of Public Health. Also, a special shout out to our colleagues at the State of Colorado Department of Public Health and Environment, who also contributed monitoring assets to this study. So, as I mentioned, we're really focused on trying to understand pad level emissions during particular operations from drilling through well completions and into the early stages of production. So if you haven't ever looked at these kinds of operations, this photograph illustrates a couple of key things. You can see here, for example, this pad undergoing drilling operations and one undergoing hydraulic fracturing operations. So you can already see that the operations, the equipment are quite different there. And of course, this affects the emissions as well. So for example, during drilling operations, you might have diesel or natural gas powered generation for the drill rigs. In our case, these were all electrified grid-powered drill rigs, taking away that emission source. But there are still important sources represented in outgassing from especially drilling mud that's used. So this is a hydrocarbon, typically based substance that's used to lubricate the drill bit and help to move drill cuttings back to the surface and can emit, as you'll see, a lot of hydrocarbons to the atmosphere. When you move on into the fracking stage, material's primarily being pushed down the wellbore, but you have a lot of power generation at the surface. It takes a lot more power than drilling to do the frack jobs. So this is more difficult to electrify. So we typically have engines here dominating the emissions. And then not illustrated here, after you go through that process, another key step often is flowback, where injected water and produced water from the formation come back up the wellbore. It's hot, it contains a lot of dissolved hydrocarbons, which depending on your control processes can be emitted at varying levels to the atmosphere. And in this study, one of the key findings I'll show you is that some of the newer practices to use closed loop tankless fluid handling systems have really helped to reduce what used to be the largest source of VOC emissions during well drilling and completions. So our study focused on the Denver-Julesburg Basin in Colorado. You heard Meredith talk a little bit about some data from up there. You can see the well distribution up here. We looked at 3 different locations across the basin. There were 4 different well pads across these 3 locations. We worked with 3 different oil and gas operators, so we had a bit of a cross-section of different practices and operation types. And we spent more than 2 years in the field following the development of these well pads to really understand when emissions were happening, how big they were, what the speciation looked like. So our monitoring assets included those from our colleagues at the state of Colorado, their Camel trailer. I'll focus on hourly speciated VOC measurements made from online gas chromatography. We also had around each well pad 2 locations where we took weekly integrated canisters for detailed VOC speciation. We also had a reference background site, typically a couple of miles away, that wasn't influenced so much by these local operations to understand the variability in regional concentrations week to week. At those 2 near pad locations, we also used continuous VOC monitors. We used photoionization detectors, which respond to a suite of VOCs and are really good at helping us pick up plumes that come across our sensors. And we use that signal to trigger speciated canisters that were filled quickly and brought back to the lab. So we had detailed speciation and concentration information about what was in these transient plumes. And key to our findings is that most of these plumes persist at a location near the pad for well under an hour, often 10 to 20 or 30 minutes. So you really need high time resolution monitoring to capture these acute exposure episodes associated with this type of plume. So we have a lot of data showing gradients at both shorter and longer timescales around the well pads. We have our 3 sites, we have different operations at those sites, and we have 50 plus VOC species. So that's way too much to look at. We'll just focus on one example to kind of illustrate some sort of typical findings. So this is a case, where we had drilling operations at our second study site. And on the left of each of these panels, the panels correspond to different groups of VOCs. On the left side, we have our background site and then our 2 near pad sites. These are the weekly concentration distributions. And if you look, for example, here at BTEX, you can see, yes, there is a local concentration increase of BTEX, even during these drilling operations here. but it tends to be fairly modest. And this is typical of what we see for the longer timescale concentration increases. On the right side of each of these panels are our plume-triggered canisters. So these are short duration samples collected in plumes. And what we typically see for many VOCs is that these concentrations are 1 to 2 orders of magnitude higher than what we see in sort of the weekly average concentrations. So these are short duration, but really high concentration plumes, often that are being advected around the site. The other thing I'll point out here is one of the things we looked in some detail at, and there's a poster this afternoon on this, was the use of newer synthetic drilling fluids. These are lower odor, making them increasingly popular choices for drilling in populated areas. We find that these synthetic drilling fluids emit a lot of longer chain alkanes. C8 to C10 alkanes in particular show up here. And the poster has a lot more detail about this. This is of interest because these compounds tend to be more reactive, so they're relevant for ozone formation. And nonane in particular also could be a concern in terms of exposure as a HAP. So one of the things we did in this study was to take all of our data collected on different timescales and look at how it compares to health guideline values for a range of different HAPs. And here we focus just in this summary on benzene and nonane. So there's a lot of information here. Again, these panels correspond to the 3 sites. The distributions correspond to different operations and different time scales. And on each of these, we have a horizontal line at a hazard quotient value of 1, where the measured concentration equals the corresponding health guideline value. So if we focus, for example, on benzene, the green distributions, these are our weekly concentrations measured at these near pad locations. And you see that the means of those, the duration of the operation, or even the individual weeks, always fall below this chronic exposure health guideline value. If you look at the yellow distributions and the blue distributions, these are coming from our triggered canisters, triggered by those plume detects, and then the hourly distributions from the camel or the blue distributions. And here you see a different story, right? We have these higher concentration, shorter duration plumes that are deriving occasional exceedances across most of the operation types for benzene of the acute health guideline value. So a lot of the interest, I think, in near operation exposure needs to be on these shorter term exposures. And this is consistent with other recent work that we published in the paper led by Yiting Ku in 2024, and a health risk assessment sponsored by the state that was more model driven in 2019. So of course, where you are relative to the pad makes a difference, right? What direction you are relative to the wind, but also the distance you are away from that. And so Donna mentioned in the session this morning, there's a lot of interest in setback distances. So one of the things that we did here was to take our observations, which, for example, at sites 1 and 2, these are our triggered canister observations. There are small black dots here that might be hard to see. Those were made mostly between about 1,100 and 1,400 feet from the pad. But we used those to constrain air mod dispersion simulations to look at what we expected the concentration profiles to look like as a function of distance. And Colorado a few years ago instituted a presumptive setback distance of 2,000 feet. And we see for these cases, by the time we project out to that distance, we're typically below the health guideline value for benzene. But these are pretty well-controlled operations. They're using electrified drill rigs. They're using closed-loop flowback systems. In other areas, these are not always common practices, and not every place has the advantage of a 2,000-foot setback distance. So if you look closer in, of course, you see that even for these pretty well-controlled operations, the likelihood of exceeding this will grow as you get, of course, closer to the well pad. So one of the things that we really need to know if we want to make predictions about the impacts, say, of future developments in a new location, are what are the emission rates of these materials coming out during different operations? You know, it's nice to go out and measure concentrations at different locations, but it's really hard to translate that into what exposure might look like somewhere else at another time. So one of the focuses of our work was to try and better constrain emission rates from these specific pre-production operations. So to do this, we took advantage of another study that we've recently been working on in the DJ Basin. This was conducted in partnership with Ajax Analytics and sponsored by the City and County of Broomfield. And here we had up to 18 monitoring locations across the community during the development of 6 large oil and gas well pads. And we basically took those concentration fields and inverted them to estimate emission rates for different operations. And I want to highlight just a few key findings from that work for you. So one is that we have what I've called here now modern estimates for drilling mud outgassing. We saw that drilling is one of the larger sources of emissions in the operations we studied. Remember, these are electrified grid-powered drill rigs, so this is primarily associated with drilling mud outgassing. If you look at EPA's oil and gas emission tool, the data there come from a 1970s study of offshore oil and gas. So to understand current conditions for both petroleum-based and synthetic drilling muds, we took a look at this. So we have data now that will be available for others to use. The second thing is we have the first VOC emission rates for a step called coiled tubing or mill-out operations. This is the step after the well is fracked. That's done in stages. There are plugs inserted to pressurize those stages, and they go and they basically mill out those plugs. And during that period, hydrocarbon vapors can escape to the atmosphere. We found this also to be a significant source of VOC emissions, and we've quantified that in this analysis. And then finally, a really interesting and important finding is that the well pads in Broomfield and the ones in the HEI measurements were using these newer closed-loop tankless fluid handling systems. And we quantified the emissions from those and compared them to prior measurements we made a few years ago of other green completions in the DJ Basin. And we found this newer technology reduces both total measured VOCs and benzene by more than 95% on average. There still are weak points. They go in and they open up sand traps that catch sand that comes out during flowback. Sand is a proppant inserted during the fracking stage, and we see pulses of emissions for short times. But overall, what used to be the largest source of VOC emissions during well completions has come down a lot with this technology. So the final thing that I'll mention, and I don't have time to go into this, is we also developed what we're calling the TRACER pre-production model. This is a simple model that's focused on these pre-production activities and is intended to be stakeholder friendly to allow you to simulate a timeline of well development and then in the model implement, for example, different best management practices to see how that impacts emissions and potential exposure. You can also do things like shift the emissions during different times of year to use different meteorology and so forth. So there is a poster about this that's being given by Da Pan this afternoon, poster number 20. If you're interested, please stop by there and you can check that out. So let me just wrap up with a few key findings. Really important, transient exposures, transient plumes are really important to look at, and they are short duration. Even hourly measurements sometimes miss these. So high time resolution measurements are key. These concentrations in these plumes can be much higher than what we typically see around the pad. So they also tend to drive the risk, the exposure risk. That's where we see exceedances, especially if you move within about 1,500 feet of even these pretty well-controlled operations. In terms of emissions, the largest benzene and total measured VOC emissions during these operations occurred during drilling and during this coil tubing mill out stage. As you saw, these newer technologies for flowback control have brought those emissions down. Those used to really dominate what we saw a few years ago. Now, at least at well pads using this technology, that has come down a lot. And then finally, if you're interested in the model, please stop by the poster and we're happy to talk more about that. Thank you.
Thank you very much. And our last speaker is Dr. Ted Russell, and he was already introduced by Donna, so invite you up.
Thank you. And it's great to be here to sort of give a brief update on some work that actually just, it was a research of opportunity in that while I was on the energy research committee, I was also part of a NASA HAQAST. This is the Health and Air Quality Applied Science Team project. And this opportunity came up to actually utilize the skills of this team, really looking at oil and gas operations. So with that, just a quick outline, but just a little bit more background is this NASA team. It's a group of about 13 different universities using Earth system products. And you can sort of think about satellites and Earth systems models that are applying these in various opportunities. And as part of this, they have this Tiger Team effort that are short term, and in this case, sort of 1 year hits where these different researchers can come together with their different expertise to really address some opportunities or specific needs. And that's what we did here. And so the idea was to use our collective talents to do this, both using models as well as satellite derived information. So what we did is we were really looking at how to extend the TRACER studies to be, look at additional basins, look at additional species, things like that you can do from space and using, in this case, some of these are larger scale air quality models, photochemical models. And in that way, we can start looking at some of the atmospheric transport and transformations over fairly large areas and to look at secondary species, et cetera, to look at some of the spatial footprints and trends over time. So what we did is, well, we sort of looked at where the TRACER studies were being done and what sort of opportunities there might be. And in particular, what we looked at was using various satellite observations coming from a couple of different satellite-based instruments. Won't get into them much right now, Tropomi and Tempo. And what they do is they have these observations from space. So what they actually give are something called vertical column densities, sort of looking down. They don't give ground level concentrations. So that's one of the places where the models really come in, is that they can relate this vertical column information to what's happening at the ground. And they can also operate to sort of allow us to understand how the atmosphere got to where it is, essentially being able to assess this linkage between sources and air quality. So that was what we've done as part of this. So first, looking at some of the modeling we've done, we used the Community Multi-Scale Air Quality Model. It's one of the most widely used EPA models. And what we did was we implemented this source apportionment technology that's called ISAM, which allows us to follow the impacts of individual sources, individual source areas, and how they have their impact regionally. And in particular, as part of this study, we looked at the various shale plays throughout the country, and we divided them into 7 different groupings such that we could look at the impact of those emissions regionally as well as somewhat locally. And I'm going to show some of those results. So first, if we look at the NOx emissions in these various areas, they show, and actually one of the things, just if you look at it, you can see that the NOx emissions in the Permian, sort of one of the bigger areas that really sort of comes out when we look at some of our results, as well as with the Eagle Ford and such. So these are the inputs that are driving our model results. We also have the emissions for all the other various pollutants that species that go into these models, including air toxics, other VOCs, et cetera. And so we simulated the different compounds of interest. This is just showing the formaldehyde and ozone, and you sort of get this, what you would expect is that you get high ozone over the urban areas, but you also sort of start seeing what's going to be of interest here is we have high ozone over the Permian, up in North Dakota, and some of these other areas. And so we can start looking at tying these back to the various oil and gas operations. And you're also looking at formaldehyde, just for those, actually that was the formaldehyde. This is the ozone. The formaldehyde, you see this big blotch over sort of the southeastern US. That's actually due to forests, but you also do see what's happening in the various oil and gas operation areas. So you are actually seeing already sort of a signal that you might think is tied to oil and gas operations. And also from these models, we were able to evaluate or sort of see how well the models correspond with the satellite observations. And so I'm showing here is how well the satellites compare. Well, this is the air quality model for this vertical column density for NO2, and also what's observed using tropomi. And you see a pretty good correlation, though there are some areas that sort of stand out that are different. It's sort of the Uinta area, somewhat in there, that may be primarily coming mainly from Mexico, but those are the sorts of things that we're looking at to better understand this linkage. So from this, we took away that we're pretty much picking up the spatial patterns, but there's some interesting differences that may indicate we're not totally capturing capturing the emissions from these different areas. So that's one of the really neat applications of combining the models and the satellite data. We also looked at comparing CMAQ results with the TRACER results, and this is looking at benzene and ozone. And so this is on your left-hand side is benzene. And what you see is actually, to me, almost surprisingly so, we were able to capture much of the mean as well as the distribution. Not quite so much scatters in the observations. That's not surprising. We get somewhat the diurnal variation, but there's some differences. We get the seasonal variation. And if you look at the 2-week average correlations, it really looked quite good. Go back. There we go. In terms of the ozone, sort of we got the average. We weren't really getting the peaks. And that's something, maybe corresponds to what Dave was talking about, is we maybe not capturing some of the individual daily variations, since we're using this annual average inventory for our work that may actually be going on that could lead to some of these peaks that we're just not capturing right now. It also could just be a pure modeling result. So then looking more at the oil and gas specific impacts using this method called ISAM, what we can do is look at the impact on ozone and formaldehyde sort of regionally. Mind you, we're using a 12-kilometer resolution, so we're not going to see much of the detail that you get to see from the TRACER model, but we do get to see the regional impacts. And so looking primarily at ozone, this gives you an idea of the impact. This is actually the maximum impact at any time. And you see it can actually go up to 35 parts per billion. That was the maximum 8-hour average impact we saw anywhere. But looking more at the seasonal average, it actually went up to 16 ppb. And you see the impact in the various plays around the country. Sort of some neat results. And then the thing that ISAM can come in is that we can attribute the impact or the ozone concentrations that we simulate to the various different processes or emission areas. And so this is the background, which you see is a substantial contribution, particularly at some of the times when you have more transport in. But you also see this is the Permian and Eagle Ford together. And you see that the impacts can be on the order of 20, 30 parts per billion, actually very much in line with what Meredith was finding. So it's sort of neat, and I think this is one of the powers of combining these various tools and using the TRACER data. We also looked at other pollutants, and these are the UOGD impacts on formaldehyde, benzene, and toluene. Not surprisingly, for things like benzene and toluene, it has very much a more local impact. But for formaldehyde, you see that you do have somewhat more of a regional impact, but certainly this local impact as well. Just getting back to looking at things from space, is that this is the Tropomi NO2. This is right in the Permian area, and you see those two peaks, formaldehyde, et cetera. And what's of interest is we can compare that with our modeling results, and you very much see these two peak areas coming together. And this is in formaldehyde, and the same thing we found for NO2. One of the really neat things, and this was my colleague Dan Goldberg did, was he used the satellite data to do some trend analysis. And in particular, he looked at various hotspots in NO2, vertical column densities around the country, both urban areas as well as oil and gas areas, and looked at how that signal changed over time. And what he found was that in most of the urban areas, the NOx vertical column density went down, or the NO2 vertical column density went down, thus leading to sort of the blue areas. But over many of the oil and gas areas, the NOx went up. And it's obvious why the NOx might go down, particularly around sort of the Ohio River Valley and some of the urban areas. You had these NOx controls. But you did see these increases over some of the oil and gas areas, though interestingly, not up in the North Dakota area. So this is one of the real powers of also having the satellite data, is we can do this trend analysis at a much larger scale. So just as a summary, this NASA Tiger team has gotten together and was able to use some of the satellite products that we're looking at, as well as the air quality modeling. And there's great agreement between the observations and the modeling. There is some bias that we still have to think about. And it's not apparent if some of these biases are more model-based, emission inventory-based, or some other issue that's going on. Overall, I think that combining the satellite observations with some of what's coming up from the TRACER teams has proven quite valuable. I will note that we're still involved in this, and we're continuing to do some further air quality modeling. So if you have some suggestions, I'm quite open to it. So with that, thank you very much. And I would like to invite all of the speakers up. But one thing while they're coming up, is just to me, looking at this, when I, as part of the research committee, have looked at really what the progress that we've made towards our goal as part of the HEI Energy Committee, was to come up with a set of tools, set of observations where we could better assess exposures. And I really think that's, if you see what they have been able to accomplish, we've really gotten quite a ways. If I look at this, the big thing now is it's time to use them. And, there's this great set of tools to help look at exposures to oil and gas operations. So with that, I'd like to sort of open the session to asking questions. Thank you. Questions for anybody? Yes. And do please identify yourself when you come up.
Harshit Kuchal, PhD student, University of Toronto. I have a question for Leah. In one of your graphs, it was pretty clear that the winds were blowing from like northeast. I am more interested in the methods that you folks use to separate the cross-boundary pollution from the local fumes.
All right, so just to clarify, the question was, so in one of my graphs, I talked about the wind coming from the northeast and how we separate the local from the cross-boundary impacts. Yeah. So in that particular, I think you're referring to a figure of measurements. So obviously in that case, we're just measuring at one location. But the northeast of the measurement location is where the well density was highest and also where there's more oil production as opposed to gas production. So part of the hypothesis was that some of the particulate pollution was from those oil wells. But to really look at where the sources were coming from, that's where we need the modeling. Do you want to?
And the only thing that I would add to that that sort of reinforces some things that Jeff was talking about with the pre-production activities was that there were new wells going in from that direction. And so I think if there's one big takeaway from this session, it's that we need really high resolution temporal emission patterns if we're going to understand these overall patterns of ambient concentrations or exposures.
A quick follow-up to that. How do you folks think about the viability of background subtraction method in this specific case?
So but think about the background subtraction method. Do you want it for the modeling? So I mean, in the TRACER modeling is really just an emissions models from oil and gas activity followed by dispersion. So in that particular case, we can model and can look at just the emissions and the pollutants from the oil and gas activity.
And there's no single answer to your question. If you're talking about a methane background correction, that's different than an ethane background correction, which is different than a benzene background correction. And the sources that you need to account for will depend on the region and so on. So there's no single answer, but there are sets of tools.
Thank you.
Chad Bailey from EPA, Office of Transportation and Air Quality. I'm entirely ignorant about everything you just talked about, but I have an anecdote that might be the basis of a question, which is that I was born in Cleveland, Ohio. My dad grew up on a farm in Ashtabula County, Ohio, which is tucked up in the very far northeastern county of Ohio. Donna's heard me talk about this a billion times. I'm probably sick of it, but my family, in the early 1980s, they had, on their farm, they had an oil well that was there, and it got closed up. And then in around 2008 or so, when oil prices peaked up, it turned on again. They had a free home heating because they just ran a gas line from their house to this, think will look like, whatever the well was, a tank that was there on their property. My uncle, who also lived nearby, drove truck for Pennzoil in like the 70s and the 80s and all around that part of Ohio and into Pennsylvania as well. And I guess I think of that as pre-shale revolution, pre-fracking revolution. This was like conventional oil and gas. And that kind of seems to overlap with where the Marcellus was. And I tend to think of Texas as kind of an oil and gas region also. So I guess my question is, do you have the ability to sort of parse out unconventional from conventional oil and gas? And it seems like the Colorado state where it was like well specific that, you do have that ability, but are the other studies, can you back out, the impact of the pre-fracking stuff that's there, like wells that have been left, closed, but still not capped or things like that? I don't know. That's my anecdote that I can give you as a question.
So if we're worried about the atmosphere and we're worried about, let's say, after the pre-production activities, the actual production activities, beyond the rate of decline in production over time, there's not all that much difference in the equipment that's actually on the surface for unconventional versus conventional. You have tanks, you have pneumatic controllers, you have all these other pieces of equipment. You have all the midstream facilities that look the same, whether it's conventional or unconventional. What's different is the subsurface. And so some of the biggest differences are going to be in activities that result in atmospheric emissions that are associated with what's going on under the surface. And that's really Jeff. So I'm going to turn to Jeff and let him talk about that a little bit.
Yeah, thanks. We do have the advantage in our study of knowing something about the operations. I neglected to mention that the operators whose sites we were studying were cooperating with the study and providing information about the operations and especially about the timeline, which was really valuable. So yeah, the type of equipment, where you're accessing, whether you're doing vertical or horizontal drilling, all these things can vary with the unconventional wells. But there are a lot of things we still don't know, like the speed of drilling, I noticed has increased a lot in recent years. And that's probably affecting the emission rates too, but we don't have a good handle on things like that. So we've learned a lot, but HEI has a lot more work to do going forward to continue to explore this space.
Yeah, thank you for your wonderful presentation. I'm Jia Zhang, Assistant Professor of Environmental Engineering at the University of Southern California. I was just curious, how did you build the collaboration with operators and oil and gas industry? And have you conveyed like your findings with the industry and local agencies? And what are the messages you gave them to improve their practice, such as like the setback distance or any other stuff? Yeah, really great work. Thank you.
So I can start there. It was really key for our study to have information about the operational details. So when we went about selecting sites, we talked to the major oil and gas producers in the Denver-Julesburg Basin, told them about our study. Many already knew about it from engaging with HEI. And to select a site for study, we required that we would have information from the operators about the details of the operations. And as I mentioned, we worked with 3 of the major operators that did provide that information. The level of detail varied. In one case, we got hour by hour drilling records that were really fantastic for timing certain things we saw. In other cases, we had sort of daily summaries, but it was much more than we would normally have available from, say, public databases about these operations. As far as sharing information, this was a discussion we actually had with HEI because we wanted to talk about what we saw with operators so we could ask them questions about operations. And normally HEI data is sort of sequestered until the study is done. So HEI gave us permission to engage with operators about details of what we were measuring and how that might relate to their activities. And we found they were often really interested in understanding this so that they could better understand how what they were doing affected their emissions as well.
And I'll reinforce what Jeff said about the importance of having that process information. These short-term variations in emission rates are driven in some cases by things like malfunctions, but in many cases by the operating practices. And so you need information about the operating practices. Over the time that we've been working, we found that it's most productive if we get multiple operators together. We can aggregate data and anonymize data. And our experience is that if we can get multiple operators together, we can get access to a lot of process information that allows us to begin to understand the observational data in the atmosphere that we're seeing in a much more robust way. So operator involvement is really key to understanding what the data mean. And our experience in working with operators is they want to make sure they're solving the real problem. And so they're hungry for information as well. And the experience we've had with the operators who voluntarily participate in studies like these. So those are my observations.
And I hate to cut off the last questions, but it is time. So with that, I'd like to again thank the panel for both for their talks as well as the wonderful work. We've been really pleased.